Okay, good morning, everyone. Let's begin our second talk of this session. The speaker is Zander Kelley from Institute for Advanced Study. He's going to talk on strong bonds for three progressions. Let's welcome.
It doesn't contain any triple of numbers which are evenly spaced. And the question is, how large can the set A be? Is this okay? Okay. Or in other words, three numbers which form an arithmetic progression. So just to be super precise about what's the central object of study here, here's just a picture of a three-term arithmetic progression. It's just a triple of numbers. And it's characterized by this simple algebraic or linear equation, just x plus y equals 2z. It tells you whether an arbitrary triple forms a three-term arithmetic progression. And we're interested in the non-trivial ones, those with x, y, and z being different. And we're saying, they're trivial when x, y, and z are the same. And we're interested in the non-trivial ones. So back to this original question. So you want to ask, how large of a set A can we pick where we avoid the inclusion of any of these non-trivial three-term arithmetic progressions? And most of the talk will be about upper bounds, but just for fun, let's talk about some lower bounds, some constructions of sets which are designed to be as large as possible while avoiding any of these three-term arithmetic progressions. Should I keep using this? Or? I can speak loudly, but it's up to you. Sure. Okay, so here's some picture from Quanta. It's just an illustration showing you, like, what if you just start from 1 and go up to n, and we just try to greedily include an integer anytime we can without adding a new 3AP into the set. And it's not terribly important, but actually you can give like a nice concrete description of what set you obtain by doing this. It's very easy to describe in base 3, for example. And you can work out that you get a set of size delta n. So it has density delta, which is this quantity here, which for this talk I'm going to call this polynomial in n density. Okay, so that's one construction. So another way you could try to get a large set with no 3APs is to pick a random set of size delta n for appropriately chosen delta. And it's not so hard to analyze this. There's only so many possible 3APs, so you can sort of just consider them all and see that one will appear with probability roughly delta cubed. So if we set delta appropriately, we can get some random construction of a set A. Also, it's going to have density, which is like polynomial in n. So now we have two constructions, both giving you polynomial density. And then finally, I'll tell you about this non-trivial geometric construction due to Barron that does substantially better. So it's going to find some set A with density delta n, where the delta is this, or the density delta is this funny-looking function here, which for the remainder of this talk, I'm going to refer to a function of this shape as quasi-polynomial in n. So Barron has this geometric idea to start with like a sphere in ZR for appropriately chosen R, full of integer points, and then it's going to carefully project down to Z in such a way that doesn't cause any additional 3APs which weren't already present to show up. And you can see why, I mean, roughly the reason this idea makes sense or why it helps is if you think about going into higher dimensions, there's this possibility of doing something which does not even make sense in one dimension, which is you could write down a set which doesn't even contain any 3 points on the same line, right? Which is a much stronger property. And then if you're careful, you need to set the parameters carefully and do this projection step carefully. You can recover a large set A with quasi-polynomial density, which still contains no 3APs. So I'll say this is, except for some lower order terms, roughly the shape of the best known constructions since the 50s, since Behrens proposed it. Okay, so now let's move on to the main subject of the talk, which is going to be upper bounds. So I first should tell you about Roth's upper bound that he proved in 1953. So he was the first to prove that these kind of sets with no 3-term arithmetic progressions, asymptotically they are actually like density 0, in the asymptotic sense as n goes to infinity. So specifically, he showed a particular bound on the density. Delta is like at most some quantity which is roughly 1 over log n, something going to 0 as n goes to infinity. So this is the first big result in this direction, and there have been since then a bunch of works on refining this upper bound, since I told you that the lower bound remained mostly unchanged since Behrens' construction in the 50s. So here is a sequence of works showing some progress. Like they're all proving a theorem of the same form. So if you have any set which is large enough density, then it must contain a 3 progression. So same qualitative result as Roth, just improving this specific density threshold that we know this to be true for. So there's works due to Heath, Brown, and Samretti. And yeah, something I will point out is that something notable about this sequence of bounds is that they're getting like ever closer to this threshold, like 1 over log n, which is an important milestone for technical and also some aesthetic reasons. But there was a big breakthrough due to Bloom and Sisask, who were able to first obtain something past this 1 over log n sort of technical barrier in 2020. And then, okay, so that was the state of the art before our work, and here's our result. So we proved that if A is a set of integers which is dense enough, then A must contain some non-trivial 3 progression, and we were the first to obtain some density which is like some quasi-polynomial quantity in n, which you can compare to Behrens' lower bound construction I mentioned earlier, which is like the same shape except for we get some different constant for the quasi-polynomial. We managed to prove 1/12 instead of 1/2. So it's an interesting question whether you can refine it further, but we were able to get this quasi-polynomial bound with 1/12. And actually, so I want to slowly sort of shift towards this other viewpoint where we're not just trying to find a single arithmetic progression. It's actually going to be more convenient to talk about just finding as many as possible. And something nice this lets us do is forget about the distinction between trivial and non-trivial solutions. So here's another form of the theorem that we proved, that if A is large enough, it has density 2 to the minus d, then it has at least this like quasi-polynomial type number of solutions to this linear equation. So this is counting both trivial and non-trivial, and this is the form I'll talk about going forward. As long as you can find a large number, then there's only so many trivial solutions, so you have found at least one non-trivial one. Sorry, so no, I guess they're both a parameter. Yeah. Yeah, if I understand your question correctly. And then, yeah, okay, so I'm slowly trying to massage this question that I started with into a more convenient form to talk about. But one thing I want to point out is that the question makes sense not just over the integers, but over other, say, finite abelian groups. You could ask, just if you have a large set of some finite abelian group, do you have a large number of solutions to this linear equation? And the answer is yes. Actually, it seems like kind of the integers are roughly the most difficult case. So actually, we are able to get a slightly better bound in this case, where you're talking about, say, like some vector space over a finite field is your group. And then, yeah, I want to say this case where the group is like this cyclic group over the cyclic group of size n is roughly equivalent to this original question we talked about, where A is a subset of integers. It's easy to translate back and forth without much loss, just from this setting to the original setting. So often I'll be talking about the problem in this form one way or another inside some finite abelian group, just for convenience for the rest of the talk. Oh yeah, sorry, I did want to say, yeah, so we proved these first 2 points. This third one is actually due to some follow-up work due to Bloom and Sask, where they showed nicely that you can get things running in an arbitrary finite abelian group. Okay. So let me start towards explaining what the approach is going to be like. So we follow this analytic approach, which mostly this is in contrast to another approach like the polynomial method, which I won't really be talking about at all. But this is kind of a very high-level summary of how all these works that I've described so far approach this problem, without getting into the specific implementations just yet. But I want to encourage you to think about the plan as a sort of hopeful reduction to one of two extreme and easy cases. So some two cases where it would be easy to show that A has a large number of solutions to this linear equation would be that if A is just some random set of size delta, then like we talked about before, then when we tried to construct one which was as large as possible, in that case, it has many more solutions, say, than Barron's set for the same kind of size, and we're content. So I'm not looking for like a strange number of 3APs. I'd be quite happy to obtain this number of 3APs you would get from just a random set. So that's a good case. Another good case would be if A was like a subgroup of this size, then certainly everything is, well, you get all the solutions you would want for this equation as well. And then this is easy to generalize a bit further. You can notice that if I take my set A and translate it by some fixed constant, that doesn't really affect whether any particular point is a solution to this equation or not. So also, this carries over to like any coset of a subgroup. And then you can sort of mix these two cases. If I zoom in on some subgroup and then I zoom in on some like random subset of that subgroup, that's also fine for like the same reasons. Okay, so those are all like, that's a collection of good cases, and in some sense we're trying to reduce to those cases. And you should imagine like we won't be able to do it in the nicest way possible because I showed you Barron's bound, right? Like that's shows you that actually these cases aren't the extreme cases quantitatively, but still like this is kind of how we're thinking about the problem. We're trying to somehow leverage some reduction to these two cases. Okay, so start by filling in a bit more details of this high-level plan. So what do we want to do? We want to like find some nice subset of our given set where it's really easy to count the number of solutions. Of course, we want it to be as large as possible, but here's like the first question is where are you going to look for this nice subset A prime? And I want to say that we're going to try to look at the intersection of A with some highly structured set V. So there's a couple different things you could try depending on the exact situation, like the exact group you find yourself in. But if I was in a group with, like, say, FQ to the n with a bunch of subgroups, I'd be quite happy to take V to be a subgroup. Maybe I'm in Zn where n is a prime and there's no subgroups, so certainly I have to try something different than that. So in the most general case, you're going to have to zoom in on some V, which is like just an approximate subgroups, which is something which is always available to you. And I want to give you some aside where I explain like a very simple version of this. So what's an approximate subgroup? So just for example, you could think of just an interval in integers. So why am I saying this is some reasonable thing to call an approximate subgroup? Well, so for some generic sets S, like a random set S, you'd expect that the number of pairs you get when you look at all the sums of pairs of elements in S, you'd see roughly S squared different things. But in contrast, this interval, how many things do you see when you take this sum set of the interval with itself? Only like 2 times as many. So in some reasonable quantitative sense, this interval is like approximately closed under addition. So that's the sense in which I mean an approximate subgroup. Okay. Yeah, so with this kind of viewpoint in mind, I want to return a bit and give you like a different way to organize these results we've seen previously. What I want to claim is that most of the work on like at least the analytic approach to this problem previously can be like factored into 2 steps. So there's this one step where you think of the high level, just generic plan that you're going to implement, all the way up to this point where I want to zoom in on some either subgroup or approximate subgroup, and then things start to get different whether you're actually in like the hard case where you need to be considering approximate subgroups, or this, people call it the model setting, like A is a subset of FQ to the N, where you have a bunch of subgroups and you can just be happy and run things with subgroups. And I want to claim that, previously there's actually not too many substantially different like overall approaches when you consider them implemented in this basic setting over here. And a lot of the work, a lot of the hard work done in these prior works that I showed you are in trying to take this approach and implement it with as little loss as possible, just get it running as absolutely efficiently as possible. And there's a ton of technology developed to do this, which we rely on heavily. So these works were important for us, for sure. I want to say, yeah, there's one other work which is like some really different idea that pushes past this like 1 over log n technical barrier, even in the simple case over here in the model setting. And then, yeah, we have this new idea that pushes past it and gets like a quasi-polynomial bound using the analytic approach in this model setting. And we really substantially rely on this past technology that was already established in order to like implement our plan in this more difficult setting using approximate subgroups. All right, so getting close to pinning down all the different aspects we need to discuss what is this analytic approach that we're going to take. So just to remind you, yeah, we're looking for how are we going to find our 3 APs that we're looking for. We take our set A that's dense. We're going to zoom in on some nice subset A prime. How are we going to find it? We take the intersection with some very structured, like either subgroup or approximate subgroup. And what are we hoping for? Well, we hope that A prime has like the right number of solutions, like, the number of solutions you would expect if A prime was actually like a random subset of this structured set B. Okay, and yeah, I'm just being like somewhat specific about what do I mean here. This is what I'm considering the right number. So like this expected number for a random set plus or minus some small like additive constant. So epsilon for this talk, you can think about it as just being some fixed constant, like 1/10. And how are we going to guarantee this? Well, we need it to be the case that A prime is in some way like pseudo-random. It has some actual specific pseudo-randomness property that guarantees that we see the right number of solutions that you would expect for a random set. Okay, and then, yeah, just to be even more specific about how are we going to do this, well, we have this case analysis plan. I mean, this is the traditional way to implement this plan, this analytic approach, that relies on this idea of density increments. So initially, we have our initial set A0 and our initial structured set, which is just G, like the full group to begin with. And then what are we doing at each step? Somehow, like if our current set is not pseudo-random, with respect to our current container set, then we want to pass to some further container set, like we restrict onto some vi plus 1. And we want it to be the case that our set has increased density inside this new container set. Okay, like at least like 1 plus epsilon, where epsilon is like a tenth. That's how you should imagine it. So some constant factor increase in density. And then, like I said, we're going to stop whenever A is pseudo-random. Then we're happy because we can count the number of solutions and control them and get what we'd like. And okay. So what do we need to do to actually implement this plan? The last thing to fill in is like we need a specific notion of pseudo-randomness that we'd like to work with. And this is where the first place where there's like a substantial deviation from prior works. Often prior works use like the size of the largest non-trivial Fourier coefficient of the indicator function of A. And here we're going to focus on some different notion, something describable in physical space rather than Fourier space. Okay. Yeah, so here is one way to describe this notion of pseudo-randomness that we're going to be interested in. I want to take two independent samples, A and A prime, from our set, uniformly at random. And here's my definition of A being pseudo-random. I want that A plus A prime to be like near uniformly distributed over our finite group G. So here's just some cartoon picture of this. And I should say for the analytic number theorists, like an apology here. I'm sorry if this terminology offends you. Yes, I'm just talking about the convolution of A with itself, or like the indicator function of A with itself. I found out that the probabilistic terminology here makes the talk reach a slightly broader audience. But yeah, that's all I'm talking about, just the convolution of the indicator function of A with itself. But I'll describe it like this. So we're interested in this density function D. We're comparing it to like the uniform density function 1 all the time. And it's just this probability density function of this random variable A plus A prime. Okay, so yeah, we would love it if it was like within plus or minus some constant epsilon from the uniform density function. It'll turn out that that's a bit too much to ask for, but first let's just say like, why is that good enough? It's somewhat clear, I promise, that yeah, if you just want to count like in any set C, what is the number of solutions to A plus A prime equals C, where C is in this set C. So this is such a strong condition that it would let you control this just for any set C at all. You would get the right answer up to some multiplicative factor. For example, yeah, for the problem itself, we'd take C to be like the set of dilates of the set A by 2. Okay, so this would certainly be sufficient. Turns out it's a bit too much to ask for, so we'll pick something slightly weaker than this, where we allow some area where we are able to fall outside of this plus or minus epsilon band. And we just want it to be very tiny. So we allow some set of bad points as long as it's really small. Set it to be like at most, think exponentially small, like 2 to the minus p, which will be some parameter that we fix shortly. And yeah, I guess we'll fix it right now. So for the remainder of the talk, I promise these are like all the 3 parameters that are going to be floating around. There won't be any more. There's just this epsilon, which I told you is just like a tenth. And then there's this P and this D. So D is controlling the density of A. And for the ultimately, for the application, we're interested in setting P to be roughly equal to D. But just for clarity, I'm going to keep them separate for the remainder of the talk, just to show you that P is telling you, the fraction of points where we fall outside of this plus or minus epsilon band. So anyway, yeah, certainly as long as this is small enough, then if we want to count the number of solutions to A plus A prime equals 2A double prime, then that's fine as long as this is smaller than the set we're interested in. We get, say, a fourth of the solutions that we wanted, which is plenty. Okay, so yeah, one last point I want to make about this. There's a roughly equivalent way to describe this condition on our density function d, which I'll write like this. So it's like the distance from our density function d from the uniform density function as measured by the p-norm. And I'd like you to take my word for it that that's roughly equivalent to this condition here, and we'll have to switch back and forth between them depending on whichever one is more convenient, but I encourage you to think of whichever one you like better as our real definition of near uniform. Okay, so yeah, so now we have talked about the definition of near uniform, and I can state the main lemma. Here it's stated for like a general finite abelian group G. So here's our main lemma of our paper. We need to prove this dichotomy that either we have this density function D and it's near uniform, and that's good for the reasons we discussed just shortly ago, that we can control the number of solutions and show that they're close to what we'd like. Or there's this alternative case where we have this density increment. We actually can find some structured set B that's not too small. That's this condition here. And where we get some constant factor increase in the density of A inside B. So that helps us complete the density increment argument I showed previously. So yeah, this is the main lemma of the paper, is this one right here. And just to show you it illustrated again, here are the two cases. There's this first case, either this density function D, it's near uniform, plus or minus epsilon, except for some small 2 to the minus p exceptional set. Or, so here's the complement case, we'll find some density increment on some large approximate subgroup B. And here's like a picture of that, so we can find not only a large set of points, but a large set of points that happen to be structured. Okay, so here's the main lemma visualized just one last time. And what's our plan, like I said, to handle this second case, which is like the bad case, is we're gonna, I'd like you to imagine that we're gonna like zoom in here until it looks like the first case. This is slightly conflating the difference between the set A itself and like A convolve A, but I'd encourage you to think of it like this anyway. It turns out to be a reasonable way to understand it. So. Okay, and then here is just, yeah, for the rest of the talk, I mean, just for some extra concreteness, like I said, this issue of subgroups versus approximate subgroups, it's not where we made our main innovation to this line of work. So actually, just for simplicity, I'm going to tell you about everything in the simple case where we have some nice model group, F2 to the n, with plenty of subgroups. And so here's the main lemma stated again, more specifically in this model setting. So what do we find? Either this density function is near uniform, or more specifically, we find some affine subspace B with small codimension where we can zoom in and get some constant factor density increment. And yeah, okay, so here I can just finish like the quantitative calculation from earlier to tell you why in this model case we get this d to the 9 bound that I promised you earlier. We can only have so many constant factor increases in the density before we reach density 1. And then the density can't increase past 1, so this is really like a termination condition. So we will find some, we'll be in this first case, like the pseudo-random case, after not too many density increments, and then the final like size of the like VT, the final structured set we zoom in onto, has this codimension bounded by roughly d to the 9. All right. Yeah, so for the rest of the talk, I'll just give you some sketch about what is our proof of this main lemma. So to begin with, the setup is roughly what you'd expect. We're just going to set up our density function D. It's the probability density function of A plus A prime. And we assume we're not in this good case, the case 1. We assume that D is not near uniform. It has some detectable deviation from the uniform density function. And somehow we need to find some large set B where we obtain this density increment here, where it has some like 1 plus epsilon density compared to the density in the ambient group. And actually, we're going to look for something stronger. So this density increment, I want to say, of the function D itself. So it's not too hard to convince yourself that this is only stronger by like an averaging argument. So if we can do this, then there's some translate of A where we can find a density increment of the same quality, the same quantity. Okay, so this is what we're looking for. And just to show you the picture again, we have our density function D, and we're literally trying to find some portion of the domain where we have some structured set B, and we get some increased density. Okay, so that's the plan right now. And there's something very bad and very unfortunate that could go wrong, like a priori at the first step. So what if, our function just looks like this? So it just, by virtue of it being a density function, it'll have deviations upward and downwards from 1. It's normalized so that's the case. But it might be that like all the upwards deviations are just like some exponentially small sliver, and then on a very small set, there's a huge downward deviation. And then like there's just no way to complete our plan. Like we really needed quantitatively like some constant factor increase in the density. So this would be like very bad before you even talk about the structure of the points where this function is above 1. It could be the case that there's just no points where it's substantially larger than 1. So that's the big issue we have to deal with first. So we have this first idea, and I want to do like a bit of a bait and switch. See why in just a second. So I want to switch from D to this function f here. So instead of looking at the density function of A plus A prime, we're going to look at the density function of A minus A prime for some reason. Well, it's going to address this problem I just told you about. And then something, that's important is that this deviation, as measured in the p norm from 1, it doesn't decrease switching from D to F. Okay, so that's necessary for us to be able to do this, but it's maybe not the main point. Let me give you the main point here. The more important point is that actually F has this property that these downward deviations from 1, as measured by the p norm, are never larger than the upwards deviations from 1, as measured by the p norm. So specifically, yeah, by switching to F, we've just like ruled out this case. F has to look like this. Like if there's some bad points downwards, then there's also some bad points upwards. And yeah, so why does this happen? Okay, this doesn't say why quite yet, but this is like just an equivalent formulation of this claim exactly. I'm just saying that this function f has non-negative odd central moments. So if you take f and subtract its mean, and then take some odd integer p and take the expectation that this is at least 0. So that's just like equivalent to the first way I expressed this statement. And then, so why is that? So it's for a fairly simple reason, just because like f is spectrally positive, as in all of its Fourier coefficients are real and non-negative. So if you're familiar with Fourier analytic calculations, you can kind of think about yourself why that means that this thing is greater than or equal to 0, but it's fairly straightforward. All we've done is like remove the trivial Fourier coefficient from the expansion of f, and then there's just like only non-negative stuff sitting around. So when you expand this big product, take the expectation, you'll get only non-negative terms appearing. Okay, so that's the proof. anyway, the reason it's important to us is because of this fact here. So that's this first main idea that we needed, is that at the very least, we can rest easy knowing that we're in this case. Like, if there's some bad deviations downwards, then there's some bad deviations upwards, and that's what we want to find. So the next issue is like whether we can find some structure in the set of deviations upwards. So it's a separate problem. Okay, and then so to introduce this second idea, I want you to think. I mean, you could imagine like our main lemma. It's like this dichotomy statement. We have to show that there's no like, there's only the case 1 and the case 2. There's no like third possible case where somehow it's like not pseudorandom, but it's also not structured. And a nice way you could imagine like generating such an example is this idea here. So you could think about this planted subspace example. You want to imagine that A is composed of some large random set, and like you take the union with some like medium-sized subspace. That's how I'm imagining it here. And you can take my word for it that, you know, if you do this calculation, it can be the case that this function f we care about, it does deviate from 1 substantially, like by some constant epsilon, like at least a 10. And the reason will be because of v. Like the random part will be fine, even though the random part is the majority of A. Like this issue that we find here, like the fact that it's quantitatively not pseudorandom, is entirely blamable on this planted subspace V. Okay, so that's how I want to talk about this. Idea here is like, even just in this hypothetical bad case, like how can you come up with a plan that would just like somehow automatically find this set V, which is, sorry, I should restate, like in the context of what our density increment argument, that's exactly what we'd like to do. We just need to find it. This isn't like a bad case for our plan overall. We just need an actual way to detect this set V and zoom in onto it. Okay, so that's what this second main idea that we use. We call it sifting, but it's some simple idea which is just to take the set A and consider a couple of like random translates of A and take the intersection of all of them with itself. And what is the effect of doing this? Well, all this like random dust, it's likely to just disappear. And then we find like not the entire planted subspace, but some of it, which we're happy with. A reasonable sized chunk of this planted subspace by doing this. Okay, so yeah, so sorry. That's our plan for finding V, at least in this like imagined bad case. So actually, we'll be doing this all the time, and it's not exactly clear, you know, if we're not in this planted subspace example, what will we find and how will it be useful? So that's what I'll explain next. So in general, what are we actually finding by doing this sifting? So we're going to do it for any A, not just this example. And yeah, so this is the setup now. We have our function f, and we assume that it deviates substantially upwards from 1, which I'm like measuring like this now. Okay. And what do? We use sifting to find some set B. It's specifically constructed like this. We take some translates of A and intersect it with itself. And what will it do? Well, it'll give us some not too tiny set B, witnessing this kind of deviation upwards from 1 of our function f. So that's the role played by B. That's what we've accomplished by doing this sifting. So let me show you this more complete picture here. So this is like sifting as a baby step towards finding this very structured set B. Remember, at the end of the day, we want to find some subspace of like structure with extremely rigid additive structure where we find a bunch of increments. And this first step is to just like find some kind of witness with a little bit of additive structure. So we find some B, and like the density function of B minus B prime is detecting this deviation upwards from 1. And then, okay, so what do we do from there? So from there we use some some existing tools in the literature. Namely like the Kreutz lemma. And that will actually get us all the way, the rest of the way there. The way I've told you the talk, or presented the talk, looks like it comes out of nowhere. Actually, this was like where we were heading the whole time. And in fact, it was known like before our work on like Roth-type problems on linear equations in 4 or more variables. It was already known how to obtain Barron-type bounds, like quasi-polynomial bounds, using this kind of tool for those problems. So somehow you can imagine that like what is this step doing? It's like transforming this problem on 3 variables to some problem on 4 variables, and then using like known techniques to get us the rest of the way there. Okay, so that's sort of the full picture of that step, and then putting the 2 steps together, you can kind of give an overall outline that looks like this for the main lemma. You start with some assumption that there is a large set C of deviations from 1. Spectral positivity tells you that actually there's a reasonably large set of deviations upwards from 1. And then sifting tells you like there's a reasonably high entropy distribution with like mild additive structure witnessing a deviation upwards from 1. And then we need some existing tools like the Kreutz lemma to tell you that there's a smaller but even much more highly structured distribution over like a structured set V, witnessing this deviation upwards from 1. All right. So that's a good summary of the entire proof outline for our main lemma. And thanks everyone.
Okay, any questions? Okay, okay. Hello, speaker. I have a questions. Actually, I have 2 questions about did you consider the aberrant variety?
Sorry?
Aberrant variety. You just for this maybe second page you consider just aberrant group. Do you consider the addition in aberrant variety or a family aberrant group?
I'm sorry, I'm not sure if I understand your question.
You consider the aberrant group? Did you consider some structure on aberrant variety?
So, are you talking about as a different question or as like a technique? So, it is an interesting idea to try to do density increments onto like a more complicated structure, like say like some ellipsoid if you were working over the integers to begin with. I don't know if that. Is your question about? Did you consider a different approach to this problem, or did I consider a different problem?
Okay, I think we can discuss later.
Sure.
Yeah, thanks for the nice talk. I have a kind of a general question. So I see your technique here is like, it looks like it's applicable for many combinatoric problems. Do you have any specific examples, like applications of it?
Yeah, so since this work, we were able to apply this to a couple of problems coming from theoretical computer science, actually. It would take me a bit of time to describe exactly what those are, but we really found out that a lot of the main techniques are really better thought of as like graph theoretic techniques on like bipartite graphs, not necessarily involving any additive structure. And we have, in these follow-up works, some similar steps. So as in there's like a spectral positivity step where you care about some positive semi-definiteness arising from the bipartite graph structure. And there's also like a sifting step where you zoom in and on some sub-rectangle and find an induced subgraph with higher density. So yes, I think that in terms of like how general is it combinatorially, I do think that it's better thought of as like technique for bipartite graphs, not really necessarily tied to the additive structure from this problem.
Okay, ask questions?
I assume there are generalizations of these results to things with more sequences, and some of these techniques could be applied there too. What I'm curious about is whether this has any applications to understanding ways to do quasi-Monte Carlo integration, where you want to avoid these kind of subsequences in the way you throw points around.
I think I might not have the background to answer that question. I'm not so sure what you mean, but I'd be happy to talk to you about it afterwards.
Okay, ask questions. Okay, if not, let's thank our speaker again. Okay.